Now we continue with the second part of lecture 22, how to use Laplace transform to solve initial value problems. So how to use Laplace transform to solve initial value problems. Okay, so I'm going to do examples. The first example is to solve the initial value problem. The third derivative of y minus the y itself equals 1. y0 is, and y prime 0, and y double prime 0, they are all 0. So this is going to be, the value 0 is going to simplify the solution a little bit. Okay, so the first step, apply Laplace transform to both sides. So Laplace transform of the third derivative of y minus y equals Laplace transform of 1. And here we use our formulas about the Laplace transform of derivatives of y. So the third derivative of y is minus the second derivative, not square, I'm sorry, minus the second derivative at 0, minus s times the first derivative at 0, minus s squared times y0, plus s cubed times Laplace transform of y. And then minus Laplace transform of y equals, and Laplace transform of 1 is 1 over s. And now, all the initial conditions are 0, so y double prime 0, y prime 0, y 0, they are all 0. So I have only s cubed minus 1 times, and Laplace transform of y, we denote by capital Y of s, equals 1 over s. So our second step is find the function capital Y of s, which is the Laplace transform of yt. So we just divide by s cubed minus 1. Our function capital Y of s is 1 over s times s cubed minus 1. And now the third step, find the inverse Laplace of capital Y, which is going to be our function. Now, capital Y is a rational function. So first, we factor out the denominator. S cubed minus 1, we can factor out as s minus 1 times s squared plus s plus 1. We need to do this factorization in real numbers. We don't use complex numbers here. So we cannot factor out s squared plus s plus 1 any further. That means we break this up into the partial fractions, a number a divided by s plus a number b divided by s minus 1. Plus, now the third term in the denominator is going to have s squared plus s plus 1. So that means in the numerator, we may have a term with s plus a constant term. Again, remember from partial fractions, the degree of the numerator is less than the degree of the denominator. So when the denominator, degree of denominator is 2, then we need to write something of first degree. And we do this because, because s squared plus s plus 1 cannot be factored further. So the last term is of the form as cs plus d over s squared plus s plus 1. Okay, now to find the constants a, b, c, d, we, on the right side, we again get the common denominator. Of course, the common denominator is s times s minus 1 times s squared plus s plus 1. So we multiply the number a with s minus 1, s squared plus s plus 1. We multiply b with s times s squared plus s plus 1, and the numerator cs plus d with s times s minus 1. If we do this, we get the common denominator. And this should be equal to 1 over this. So the numerators should be equal. So a times, if I multiply s minus 1 with s squared plus s plus 1, I get s cubed minus 1, plus b times s with s squared plus s plus 1, so s cubed plus s squared plus 1. And then cs plus d times s squared minus s. This should be 1. So as cubed minus a plus bs cubed plus bs squared plus 1 plus cs cubed minus cs squared plus ds squared minus ds is 1. So a plus b plus c times s cubed plus b minus c plus d s squared. Okay. Oh, I made a mistake here. S times s squared plus s plus 1. So s cubed plus s squared plus s. So plus bs. You see, you need to be real careful when you're working this out. Okay, so with s, I have b minus d times s, and the constant term, we have only minus a equals 1. Let's see, how many terms do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. Yes. Okay, so a plus b plus c should be 0. B minus c plus d is 0. B minus d is 0, and minus a is 1. So from these 4 equations, we get a equals minus 1, and from the third equation, d equals b. So we use them in the first 2 equations. Use them in the first 2 equations. We have, okay, let me do it over here. A is minus 1 plus b plus c is 0. And in the second equation, b minus c plus d, but d is also b, equals 0. So from these 2, I have b plus c equals 1, 2b minus c equals 0. So if I add them up, I have 3b equals 1. So b equals 1/3. And b is also equal to d, remember. And what is c? C is 2b from here. So c is 2/3. So finally, this means my fraction, let me go like this. My fraction, what was my fraction? 1 over s times s cubed minus 1. A is minus 1, so minus 1 over s. B is 1/3 plus 1/3, 1 over s minus 1, plus D is 1/3, C is 2/3. So if I take out the 1/3, for C, I have 2, so 2s. For D, we have 1. 2s plus 1 over s squared plus s plus 1. Okay, so this is my function. This is my function, capital Y of s. So now we need to find its inverse Laplace. So inverse Laplace of capital Y of s. Inverse, so minus inverse Laplace of 1 over s plus 1/3 inverse Laplace of 1 over s minus 1 plus 1/3 inverse Laplace of 2s plus 1 over s squared plus s plus 1. Now, we know that 1 over s is the Laplace transform of 1. So this means inverse of 1 over s is 1. 1 over s minus 1 is the Laplace transform of e to the t. So inverse Laplace of 1 over s minus 1 is e to the t. Now the last one is a little bit tricky. Not tricky really, but we need to do some work. Okay, so 2s plus 1 over s squared plus s plus 1. Now you see, in order to see this as the Laplace transform of something, I shouldn't have this s term. I need something squared. This is going to be either sine or cosine, right? Okay, recall. Let me open a box here, recall. Laplace transform of cosine AT is s over s squared plus a squared. Laplace transform of sine AT, a over s squared plus a squared. But we have this term s. So what we are going to have is a translation. We try to write this, we complete this to a square. Again, this follows, think about this as integration. If you have this rational function, and if you're trying to integrate it, when you cannot factor it out, s squared plus s plus 1, we cannot factor it out any further, we try to complete it to a square. So we try to write s squared plus s as square of s plus, since coefficient of s is 1, I need to take square of s plus 1/2. If I take the square of s plus 1/2, I have s squared plus s plus 1/4. But on the left side, I have plus 1. So I need to add 3/4 to this to get plus 1. So this is going to be like 3/4 is going to be like a squared in sine or cosine. But here, instead of s, I have s plus 1/2. So when do we get, instead of S, when do we get a translate? Instead of S, we get S minus C. If you remember this, if you multiply a function with the exponential function, e to the at, if you multiply it with a function, its Laplace transform is going to be the Laplace transform of f, but we translate s by a. So instead of s, we get s minus a. Remember this again from lecture 21. Okay, so we need to consider, so this function has s plus 1/2. So this 1/2 is like this a here, so minus 1/2. But we need to see the same thing. We need to consider the whole function. In the whole function, we need s plus 1/2. So since I have s plus 1/2 in the denominator, I should have the same in the numerator. So in the numerator, instead of s, I try to have s plus 1/2. But it is not s plus 1/2, it's just s. So I also subtract 1/2 plus 1. So 2 times s plus 1/2, and 2 times minus 1/2 is minus 1 plus 1. So that term cancels out. We are lucky, but if it doesn't cancel out, so we separate it into 2 parts then. One of them is going to be sine, the other is going to be cosine. But in this case, it cancels out. So we have 2. This is a coefficient in front of all thing. S plus 1/2 divided by s plus 1/2 squared plus 3/4. So I try to see this, so 2 is constant, f of s plus 1/2. And what is my function f of s? It is s over s squared plus 3/4. So in the function s over s squared plus 3/4, I replace s with s plus 1/2. Now this function, s over s squared plus 3/4 is the Laplace transform of cosine square root of 3/2t. Remember, in cosine, we have s over s squared plus a squared. So the number a is the square root of 3/4, or root 3/2. So when I replace s with s plus 1/2, we have Laplace transform of e to the power minus 1/2 t. You see, it's, okay. It should be s minus a. So since I have s plus 1/2, it means this a is minus 1/2 t cosine root 3/2t. Okay, so finally then, this last term, what is my last term? Yeah, so last term, 2s plus 1 over s squared plus s plus 1. So I write it as 2 times s plus 1/2 divided by s plus 1/2 squared plus 3/4. So this is 2 times Laplace transform of e to the minus t/2 cosine root 3/2t. So this means Laplace inverse of this is e to the minus, 2, I have a 2, 2 e to the minus t/2 cosine square root of 3 over 2t. Since the Laplace transform is linear, we can put the constants in or out of the Laplace transform or its inverse. So finally, my solution is the Laplace inverse of the whole function. Remember, it has 3 parts. So in the first part, we have Laplace inverse of -1. So minus, wait a minute. Okay, let's go back up. Okay, so in the first part, I have 1 over s, I'm sorry, minus Laplace inverse, so I have -1. And then plus 1/3 so -1 plus 1/3 plus 1/3 times inverse Laplace of 1 over s minus 1, which is e to the t. Plus, again, 1/3 times inverse Laplace of the last term. So this is 2 e to the minus t over 2 cosine square root of 3t over 2. So this is the solution of our differential equation, our initial value problem. Let's try to find, let's try to see the connection with what we have done before. So let's remember, let me rewrite, just one moment. Let me rewrite the problem. So what is the problem? I'm sorry. Yeah. Remember, the problem is the third derivative of y minus y equals 1, and we have initial conditions. Now, of course, we can find a general solution of this equation. If you remember, we first find, this is a linear equation, so first we find solutions of the homogeneous equation, and so the solution of the homogeneous equation, plus we find a particular solution. So in this solution we obtained, this constant -1 is our particular solution. Okay, if you take your function to be constant -1, the third derivative is going to be 0, so minus the function is going to be 1. And then the functions e to the t, e to the minus t over 2 cosine, they come from the solutions of the homogeneous part. So since it is of third degree, its characteristic equation is s cubed minus 1 equal to 0. So s minus 1, sorry, we don't use s. What were we using? Lambda. Lambda cube characteristic equation, -1 equal to 0. So lambda minus 1, lambda squared plus lambda plus 1 equal to 0. So first we obtain lambda equals 1. From this solution, we get the solution e to the t. And from the second factor, it doesn't have real solutions. It has complex solutions. So we have e to the minus t over 2 cosine, and we also have e to the minus t over 2 sine. But remember, we also have the initial conditions. So the general solution is going to be of the form -1 plus c1 times e to the t plus c2 times e to the minus t over 2 cosine root 3t over 2 plus c3 e to the minus t over 2 sine root 3t over 2. And now to find constants, we use the initial conditions. And you see, when you use the Laplace transform, it does both of them at the same time. So it finds the general solution together with the constants. So you don't need to write the general solution and then use the initial conditions to find the constants. You see the constants, this is 1/3 is your C1, this 2/3 is your C2, and C3 is 0, as we understand from this solution. But using Laplace transform, you don't need to go through these steps, but you see the parallel. You see this characteristic equation is the same as this denominator here. The factors of the characteristic equation appear in the denominator of the Laplace transform. So see the parallels and compare using Laplace transform with our earlier methods. So in this case, okay, maybe we did some work, but in order for you to understand how we obtained the inverse Laplace transform, I try to include more details, but when you are working it out, you don't need to write this many details, especially to find the inverse Laplace of the last term. Once you understand how it is done, from this step, you write your function in this form, and then you can immediately see that it is the Laplace transform of this function, so you don't need to give the other details. Whereas with our previous methods, first we need to write the general solution, and to write the general solution, we need to find the roots of the characteristic equation, and then using the initial conditions, we need to find the constants C1, C2, C3. And however you look at it, it means solving 3 equations together. You might say in using the Laplace transform, we also solved equations to find these constants. Where am I? Yeah, we again solved the equations to find the constants A, B, C, D. Well, you just weigh one with the other. The main use of the Laplace transform is coming up next in the third part. It's so with these examples, our previous methods also work, but Laplace transform gives us a way to work out, find the general solution together with the constants. So it does it all at once. So in this way, you may prefer to work with the Laplace transform. I said part 3, but maybe I can make an introduction. So basically, I don't want to go over this example, but remember the steps. First, apply Laplace transform to both sides. Use Laplace transform of derivatives and also use the given initial conditions, and find the function capital Y of S by solving the equation. And the main thing is to find the inverse Laplace of this function. And to do this, we use partial fractions. We separate our rational function into partial fractions, and for each partial fraction, we find the inverse and combine them all together using linearity. But the main thing with Laplace is that we can use it on step functions. So the main use of Laplace transform, not main use, another use, let's say, because as in the previous example, we can also use it when we can also use our previous methods. Another use of Laplace transform is when the function on the right side of our differential equation, of our linear differential equation, has discontinuities. Or simply when the function is partially defined. What does it mean, partially defined? For example, you have a linear differential equation, let's say second derivative plus minus the first derivative plus 2 times the function equals a function g of t, where g of t is not elementary. Let's say it is given as, I don't know, say t squared plus 1 if t is less than 1, and let's say t cubed if t greater than or equal to 1. So we should say simply when the function is partially defined, not elementary. Okay, so our previous methods, at least they don't work directly. You can still use them in different intervals. You can consider the intervals separately for t less than 1 and then t greater than or equal to 1, and try to glue them together as a function like this g. But Laplace transform, again, works in this case, works both sides at the same time. The interval for t less than 1 and for the interval t greater than or equal to 1 in this example. So we can use Laplace transform in this case. Okay, so to do this, first we define unit step function at time t equals some constant point c. We are going to consider positive, because remember, for Laplace transform, we consider integral from 0 to infinity. So everything takes place on positive real numbers. So we take a positive number c. So unit step function at time t equals c. C positive, a constant. 1 to square root of 2 e root 2 over 2, something like that, a constant number. First we define this unit step function. Units, so we denote this function by small u. To indicate the value of c, we use c as a subscript, uc of t. And this is defined to be as 0 if t is less than c, and 1 if t greater than or equal to c. So it is as I said, we only consider positive values of t. So for t equals c or greater, it is 0. Maybe I can use another color. And for t less than c, it is 0. Okay, so this is a unit step function. Of course, you can take it to be 0 for negative numbers also, but basically for Laplace transform, we need positive numbers, but no harm done. You can take it to be 0 for all negative numbers. Okay, And for t greater than or equal to c, it is +1. That's unit step function. Now, this function is continuous, piecewise continuous. So uc of t is piecewise continuous. Only one discontinuity, piecewise continuous with only discontinuity. At time t equals c. And we use this unit step function to write other partially defined functions in a more compact form. So we use unit step functions to write partially defined functions. I'm going to do this in examples. Okay, I'm not going to give you the general form, but explain how we do it in examples. For the general form, you can look at, again, you can look at the lecture notes. Okay, so for example, let's say we have the function g defined to be t if t is less than 1, and t squared plus 1 if t is greater than or equal to 1. How can I write this function g using unit step functions? So first, t, so 1, 1, 2, again, let me change my color. So up to 1, the function is just t. So the graph is like this. You can also consider it for negative t, doesn't matter. For t equals 1 or larger, it is t squared plus 1. So it is at 1, it becomes 2, and then it is a parabola type of thing, something like this. Okay, so again, the only discontinuity is this function is piecewise continuous. Only discontinuity is at t equals 1. So we use unit step function at t equals 1. Let's remember what is u1 of t. It is 0 if t is less than 1, and 1 if t is greater than or equal to 1. All right? Okay, so for t less than 1, we want our function g to be t. So for t less than 1, we just take the function t. For t greater than or equal to 1, we use the unit step function. But if I use it with t squared plus 1, for t greater than or equal to 1, in this formula, we also have t. But for t greater than or equal to 1, in my function, I should have only t squared plus 1. So I subtract t. So basically, I start with the function t, and then plus I use the unit step function at t equals 1. I take the second function for my function g in the interval t greater than or equal to 1, and I subtract the function t. Okay, so let's see if g is really equal to this. For t less than 1, my function u1 of t is 0. So this expression t plus u1t times t squared plus 1 minus t, u1 of t is 0, so this is going to be just t, which is the same as my function g. Now, if, if t is greater than or equal to 1, if t is greater than or equal to 1, then u1 of t is 1. So the expression t plus u1 of t, t squared plus 1 minus t is going to be, I have t plus u1 of t is 1. You see why I need the minus t here. This minus t cancels the plus t, so I have only t squared plus 1, which is my function g. All right, so I write my function g using the unit step function at t equals 1 in this way. All right, so I start with the first function, t, use the unit step function at 1. I take second function minus the first function. Now, similarly, if I have, as another example, if my function g has more discontinuities, say 0 if t is less than 2, t minus 2 if t is between 2 and 3, 4 minus t if t is between 3 and 4, and 0 again if t greater than or equal to 4. So we start with 0 plus. The first discontinuity is at 2, so we take u2, second function t minus 2 minus the first function 0. Next discontinuity is at u3. So for t greater than or equal to 3, I have 4 minus t minus the previous one is t minus 2 plus the next discontinuity is at 4, so u4, last function 0 minus the previous function 4 minus t. So I have u2t times t minus 2 plus u3t times 4 plus 2 is 6 minus 2t plus u4t times 4, t minus 4. Okay. So I hope you see the general pattern of how to do this for partially defined functions. Of course, discontinuities may be infinitely many, then you may have an infinite sum, but basically this is how we go. The first function plus unit step at first discontinuity, the function for t greater than discontinuity minus the function for t less than discontinuity. And we keep doing the same thing until we reach the last discontinuity. Okay, and now we can figure out Laplace transform of such functions and use it to solve differential equations when the function on the right side is, like in these examples, a partially defined function. And that we are going to do in part 3. So that's all for part 2.